So this at a high level is how hyperparameter tuning is carried out. Let's now understand the nitty gritty. Let's click on the hyperparameter IPython notebook. Once again, we are not actually going to execute this code because, as it says right up here, this code is going to take several hours to run even on the cloud. But let's go through and understand each of the steps. We start pretty much as usual by setting a bunch of environment variables, nothing too different here. We then need to specify the command line parameters correctly. These need to include values for all of the hyperparameters. So this is important for us to get right. The only way that ML Engine will be able to help us tune a particular hyperparameter is if we accept that particular hyperparameter's value from the command line. So that's what we see done here using the parser.add argument method. Next on the agenda, we've got to give our experiment a way in which to evaluate different models that are being tuned. And this is done by adding an evaluation metric. Notice how this evaluation metric has a particular name. Training/HP tuning/metric. This is in addition to the RMSE evaluation metric which we had already given. That will be used while comparing different epochs or different versions of the same model. If you want to compare different models, then the metric that we are going to specify has the name training/HP tuning/metric. In this particular instance, we specify the same metric for both of these evaluations. So in both the RMSE as well as the hyperparameter tuning phase, we make use of the metrics.streaming root mean squared error. The next thing that we've got to do, we've got to ensure that the different models all get serialized into different directories. Recall that in the experiment framework, we specify the output directory to which our model should be written. So far, we've just been specifying the one output directory that would have had the effect of overwriting previous versions of the saved model. Now we are going to change that output directory so that there is a separate directory for each configuration and each trial. Notice how while doing so, we make use of the environment variable tf_config. This is going to be set for us and it will be updated by the system, that is by Cloud ML Engine. And in this way, we can use tf_config as a suffix into our output directory. This will make sure that different model configurations get serialized into different directories. Notice also that in addition to this, we also tack on the particular trial that we happen to be executing. This is a way of making sure that multiple trials all end up with unique names. And now perhaps the most important part of this entire hyperparameter tuning process, which is defining the hyperparam YAML file. Once again, YAML is just a simple markup format. It's an acronym for yet another markup language. Within this config file, we specify different properties, such as for instance the scale tier. Notice how we've changed the scale tier from basic to standard 1. We then have a hyperparameter section in which we specify the maximum number of trials. This is 30, followed by the hyperparameters that we actually want to tweak. In this instance, those hyperparameters are 3. They are the training batch size, the number of buckets, and the number of hidden units. Let's very quickly examine each of those 3 hyperparameters, starting with the training batch size. We are instructing the ML engine to try different values from 64 to 512, vary those values in an intelligent way using a unit log scale. The next hyperparameter is the number of buckets. Once again, this is an integer. Once again, we'd like to try different values between 10 and 20. This time, a unit linear increase is fine. Third parameter is the number of hidden units. This is categorical. Notice how we specify different combinations. The first of these has just 2 layers with 128 and 32 neurons respectively. And the other 2 configurations which we are going to try have 3 layers with differing numbers of neurons. And Cloud ML Engine is smart enough to figure out these strings and parse those strings and convert them into the number of units which we are going to need to specify in our deep and wide model. Once we are done setting up this hyperparam.yaml file, we can go ahead and invoke the distributed training service of Cloud ML Engine. Notice the big change this time is that we specify a config file. That config file, of course, is the hyperparam.yaml. And notice that Cloud ML Engine is going to be smart about choosing only 30 different trials. Remember that that is the max number of trials that we had specified in our config file. Within these 30 different trials, it's going to try various model configurations and come back with the best. Once again, we don't actually execute this code because of how computationally intensive and how expensive it is. But we do know from the Google material that this hyperparameter tuning causes the RMSE to fall from 8.3 to just 5. That's a big improvement. And at this point, we could really go for maximum. We could improve further the performance of our model by carrying out that training on the full data set, on all of the 2 million rows available to us in the public data set. This is not something that we are going to try. You can see that the Google material warns us that this incurs a significant expense. But if we did actually go ahead and run this, we can see from that material that the RMSE falls even further from 5 to 3. So clearly, the so what of this whole experiment was that the magical results that we wanted from machine learning were really only obtained once we added distributed training, hyperparameter tuning, and ran all of this on the cloud with really large data sets. That is what caused our root mean square error to fall from around 9 at the start of this process very quickly down to 3.